Learning Task 1.1, Chapter 2, Question 2.12. The 4fc times the quantity of x squared minus y squared orbital has the angular function y equals to constant times c times the quantity of x squared minus y squared divided by r cubed. A, how many radial nodes does this orbital have? B, how many angular nodes does it have? C, write equations to define the angular nodal surfaces. What shapes are these surfaces? And sketch the shape of the orbital and show all radial and angular nodes. So for letter A, to calculate the number of radial nodes, we will use this formula. Radial nodes is equals to n minus I minus 1. In this orbital, the value of n is 4, while the I for F is 3. So radial nodes is equals to 4 minus 3 minus 1, which is 0. Therefore, the orbital does not have any radial nodes. For letter B, the number of angular nodes is the same as the number I, which for F is 3. So this orbital do have 3 angular nodes. For letter C, in order to define the surfaces of the angular nodes, we have to equalize the numerator of a fraction with 0, which will be z times the quantity of x squared minus y squared equals to 0. In this case, we have two options. The first option is z equals 0, while the second option is x squared minus y squared equals 0. This will give the x squared equals y squared. Getting the square root, it now becomes x equals to positive negative y. Hence, the solution are z equals 0, xy plane, and the planes where x is equals to y and x is equals to negative y, both perpendicular to the xy plane. When x is bigger than y, the function is positive, and otherwise it is negative. And if z is equals to 0, the angular surfaces are in the xy plane. For the shape of the orbital, there are 8 lobes, 4 above and 4 below the xy plane. Down the z-axis, this orbital looks like the x squared y squared orbital. But the node at the xy plane splits each lobe into 2. Chapter 3, question 3.36. Although the carbon fluorine distances and the fluorine carbon fluorine bond angles differ considerably in tetrafluoroethylene, carbonyl fluoride, carbon tetrafluoride, and the anion of F3CO. The fluorine distance in all 4 structures is very nearly the same, in which it is in between the range of 215 to 280 ppm. Explain using the LCP model of Gillespie. In this table, we can see the steric number, carbon fluorine length in PM, the FCF angle, and the fluorine length in PM for tetrafluoroethylene, carbonyl fluoride, carbon tetrafluoride, and the anion of F3CO. Ligand close packing, or the LCP model of Gillespie, assumes that ligands are tightly packed around the central atom. Furthermore, it also assumes that the total distance between dependent atoms is the total or the sum of all the radii of dependent atoms. Hence, the distance between dependent atoms of a certain compound is quite similar depending on the radii. In this problem, the LCP model views the fluorine ligands as hard objects that are tightly packed around the central carbon atom. The fluorine-fluorine distance remains nearly constant while the central atom moves in order to minimize propulsion. Chapter 4, question 4.6, determine the point groups for F, the possible isomers of tribromobenzene, G, a tetrahedron inscribed in cube in which alternate corners of the cube are also corners of the tetrahedron. H, B3H8, I, a mountain swallowtail butterfly, And J, the Golden Gate Bridge in San Francisco, California. F, the possible isomers of tribromobenzene is 1,3,5-tribromobenzene, 1,2,3-tribromobenzene, and 1,3,4-tribromobenzene. First, 1,3,5-tribromobenzene has a C3 axis perpendicular to the ring and 3C2 axis perpendicular to the C3 axis at each carbon atom without a bromine relative to the center. 1,3,5-tribromobenzene has a horizontal mirror plane, sigma H. Thus, it is classified as D3H. Second, for 1,2,3-tribromobenzene, it has a C2 axis, collinear to the second bromine, and a horizontal and vertical mirror plane centered at the Z axis. Thus, it is classified as C2. Lastly, for letter F, 1,3,4-tribromobenzene only has a horizontal mirror plane, sigma H. Thus, it is classified as CS. G, a tetrahedron inscribed in a cube, has 4 C3 axes collinear with each head of the tetrahedron and 3 C2 passing through opposite spaces of the central point, 45 degrees each line connecting each head. Tetrahedrons also have 6 mirror planes, sigma D, collinear to each of its C2 and C3 axes. Therefore, a tetrahedron is classified as a high symmetry group TD. H, B3H8. B3H8 has a C2 axis passing straight through the boron atoms and 2 other C2 axes perpendicular to each other and to the previous. B3H8 also has 2 mirror planes, each collinear with each of the outer HBF planes, classifying it as B2D. A mountain swallowtail butterfly only has one plane of symmetry, which is cutting through the head down to the end tip of the abdomen of the butterfly, separates the left and the right side. Therefore, it is classified as BCS. Lastly, the Golden Gate Bridge in San Francisco, California, has two C2 axes perpendicular to each other, and one of which is collinear to the length of the bridge. The bridge also has 2 mirror planes collinear to the axis mentioned, which classifies the bridge as C to V. Chapter 5, letter B for letter B, how does your diagram illustrate the difference in electronegativity between nitrogen and oxygen? So this is the diagram for nitrogen and oxygen. O is more electronegative than N, so its orbitals are slightly lower in energy. The bonding orbitals are slightly more concentrated on oxygen.